pre-calculus students, today I'm going to keep my voice down a little bit because some of my class is working on a quiz. So what we're going to do is we're going to briefly go over polar coordinates again. We'll start with some of the pre-calculus ideas, and then we'll move along and get to where we define the derivative in polar coordinates today. So I thought I'd just remind you of where polar coordinates come from. Remember, they have a pole and an angle instead of like a horizontal and a vertical displacement, like Cartesian coordinates. So I like to always just go back to a simple triangle to remind myself where the conversion equations come from, because they're very simple if you know stuff about basic trig. So in the Cartesian coordinates, this point would be labeled xy. In polar, the only reason I even think about the x and y axes to begin with is because they're kind of like a frame of reference that I'm comfortable with, but I'm not thinking about horizontal and vertical displacements. I'm thinking about angles from the positive x-axis, or from here, and then how far out I am in concentric circles from the pole. So how can I convert that into polar coordinates? Well, it's pretty simple. You just think about an arbitrary angle. I drew a nice easy one, right? And I think about, well, I'll call this distance r. And then I say, well, if that's r, how far is this?
X.
This is x, and this is
Y.
and we'll call the angle theta, because that's usually the letter we use. Yeah, then we just use Pythagoras. So one of the conversion equations is Pythagoras. It's r squared equals x squared plus y squared, except it's usually written like this. But, I mean, if you want to write it the other way, that's, of course, plenty acceptable. One of the other equations shows you how to convert directly from x to the polar version. And to do that, you just think about your basic trigonometric ratios. Consider the cosine of theta. Cosine of theta is x over r. So that says the rectangular x is in fact the polar r cosine theta. If you consider the sine of theta, you're going to see that that's opposite over hypotenuse, will be y over r. So y, in other words, is r sine of theta. And there you go. So if you want to write those down as conversion equations, you can. There's one other conversion equation which is useful especially in vectors, but it comes from that same place, nowhere mysterious, and that is
Arc sine? Arc cosine?
theta you can get by using an arc function, usually the one that's considered as arctangent, but you're right as well, Katie. So theta would be the arctangent of y over x, right? Or sometimes that's written as tangent of theta equals y over x. So those are your basic polar conversion equations that you might need to use even in polar calculus. Polar calculus is kind of a big deal. The polar coordinate system is really big, especially in Calc 3. So we're going to start looking at it this year. Alright, so let's do some nice pre-calc problems really fast. So what if you have the polar coordinate 2 theta? How could you change that into good old normal Cartesian coordinates? You could go...
Just plug it in.
You could plug in where?
R times cosine.
Oh, couldn't you go r cosine of theta? So x you could just pop out right away. Isn't it just r cosine of theta? What's the cosine of pi?
-1.
X coordinate over here is -1, so that's -2. Same thing with y. Sine, or the y coordinate over here at pi radians,
0.
is 0, so that is 0. So in Cartesian coordinates, the polar point 2 theta is x equals -2, y equals 0, so it's over there. That should make sense, I think. Let's do another example. So what if we have polar, what if we're out a radius of about 1.7 or the square root of 3 and our angle is 30 degrees? You can just do this the same way, right? X equals r cosine of theta, y equals r sine of theta. Do those with a nice unit circle calculation. Pi over 6 is 30, 1 square root of 3, that's a 3. So this is going to be square root of 3 times the cosine is square root of 3 over 2. This is going to be square root of 3 times the sine is 1/2. So the y is square root of 3 over 2, and the x is 3/2. There you go. So the polar, that is the Cartesian 1.5 horizontally, square root of 3 over 2 up. Cool? There you go. Let's go backwards with one just so we can remember how to do that. So what if we have xy equals negative 1, 1, and we want a polar representation of that point?
R is the square root of 2.
R is the square root of 2. Where is that coming from?
The Pythagoras thing.
So Katie's going to Pythagoras, she's going to this one, and saying the square root of negative 1 squared plus 1 squared is the square root of 2. She's got R. How could she come up with theta? Because we need R and theta for going into polar.
Just take the arctangent of 1, make it
So we
1.
could say, you could start out by just saying tangent of theta equals y over x. Or you could do it like I have it right here and say, that's the same thing as if you operate on both sides with arctangent and say, okay, where is the tangent equal to negative 1? I don't think that's at actually one of the corners in our system. It's actually a triangle. Don't we think of it like this?
It's 5
Arctangent lives there.
pi over 4.
It's 45 degrees right here. Negative 5, 1, square root of 2. So technically it's not, if you put this in your calculator, it's not going to tell you 5 pi over 4. 5 pi over here, 4 is over here, by the way. This is 7 pi over 4, but your calculator won't tell you that because that's not where the original arctangent lives. It will tell you negative pi over 4, exactly. So, is the polar version of this, square root of 2, negative pi over 4, the only polar version of that?
No.
The answer is no. This spot that's out square root of 2, which you can see kind of nice right there, yeah? You know what I'm saying? There's other ways to express that. For every Cartesian coordinate, there's an infinite number of polar versions. Give me another polar version of this that's equivalent.
Square root of 2, 7 pi over 4.
There you go. So you can use that aspect of trigonometry. Give me a one like that.
3 pi over 4.
Katie says 3 pi over 4, so this is that true or not? If you go to 3 pi over 4, you go here. Positive square root of 2 would be there. Negative square root of 2 flips you over the pole. She is correct. And there's, of course, lots and lots of an infinite number of other representations. Okay, let's also review some very basic polar graphs before we do some polar derivatives. Okay, r equals 6. What does that look like as a graph? It says the only thing that has to be true is the radius has to be 6. That's a circle. Circle, what kind of circle, Sam? Centered at the origin, attached to one of the sides, because all those things are polar possibilities.
Centered at the origin.
I think it's centered at the origin, and this is supposed to be 6. A basic
Also,
circle.
if we get like this.
I think that just has to do with the step size that you're selecting. We're going to start talking about that though,
Big
Katie.
step or little step?
So I'm not going to, it has to do with the step size. So let's keep going because we don't have too much time today. If the angle is the only thing that's specified and it says the angle is 60 degrees like this one, what would that mean? Well, that means that that's about at 60 degrees, that's about at 60 degrees, that's about at 60 degrees. That means this is your equation. So how do you figure out what it is? It's a line through the origin. If you want to figure out the rectangular version, then you'd go and use one of those, and you could say, oh, theta equals the inverse tangent. You know what? I don't like using that one for this. I'm just going to like operate on both sides of this guy and say the tangent of theta equals the tangent of pi over 3. What's the tangent of 60 degrees here? Opposite over adjacent. So that says Tangent of theta equals square root of 3 over 1. What's tangent of theta equal to from our conversions over there? Y over x. So it says y over x equals the square root of 3 over 1. If you want to change that to a line, then multiply by x. The slope of your line is square root of 3. So that should make sense. This one likewise, I mean, you can just go over there and to the top equation, you get square root of x squared plus y squared equals 6. Square both sides, and you get x squared plus y squared equals 36, your standard circle. Okay, how about this last one? Can you guys help me convert this, and we'll think about what its picture is?
Multiply both sides by sine of theta.
I think on this one I would go r equals 4 over sine first. Just a nice basic identity, and then I'd do what Sam said, and multiply it up to this side. And then I'd be like, oh, that's just y. Oh, this must also just be a nice basic line that's 4 high. Okay, so there's some nice basic polar graphs. We're of course going to look at some more interesting ones. So the next thing I wanted to do was show you how polar and parametric are related, because in order to take a derivative in polar we need to know that. Okay, we're going to rely on how those two things, how those two coordinate systems are related in order to take a derivative. And also, of course, in order to think about this graph. So I want to think about the graph of 1/2 theta. So how do I figure out the graph of 1/2 theta? It seems pretty simple, just like those other ones, but actually this is a much more difficult graph to figure out. It just happens to be that way. Those other ones didn't take a whole lot of thought. This one you might think is the same, but it's not really. So I'm going to rely on how to go from polar to parametric. So parametric had like x and y, right? And it had like x was like some f of t. Since this has a theta in it, maybe I should just go theta for my parameter here. You guys feel me? And then y is going to be like f of some other, well, the same parameter, theta. You can put t if you want, but we got a theta already, so I'll use some theta. Okay, so, so something is here. Isn't r actually up here? Couldn't we say that this is like, for our example, r is like f of theta already? Isn't this like an f of theta? So what's the only thing that you have to do here? I think the idea is that you've got to go like this. You're going to have to go, I'm thinking, yeah, I'm good. So what was the conversion to go from Cartesian to polar again? We just had it up on the board, I erased it. X equals
R cosine. R sine.
And you have what r is.
and I put these together. And for our specific example, what was r, or in other words, what was f of theta? Just like what you're mouthing, Kylie. And now we have it in parametric mode. So this is nice for a lot of reasons. For instance, if your machine or your software didn't have a polar graphing mode, but it did have a parametric graphing mode, you could now stick this in your calculator and graph it. Let's go ahead and do that. But this is also fundamental, this kind of expression right here, this f of theta, cosine of theta, f of theta, sine of theta, for us figuring out how to take a derivative. I don't think it's much of a leap of faith to figure out how to do a derivative. Let's graph this really quickly though. So 1/2 theta cosine theta, 1/2 theta sine theta, what's that look like? I'm going to go and make mine parametric, looks like it is. Go to y equals. Now of course we could just put this in polar mode, but I'm just showing you the idea here. Now we might be getting some different answers based on our window, right? We've got to run the parameter a long way, so I'm going to go negative 10 to 10 by 0.1. That's a pretty good way. I'll probably get a lot of the graph if I do that way. I ran my parameter a farther way. So if you want to zoom out a little bit, you might see that there's more to this curve than at first meets the eye. This is a spiral polar curve. And you can see it. Do you think it's going to continue or go back and trace itself based on what it did so far? Probably going to continue. Let's see.
Mine's different.
Yeah.
Depends on what your parameter range is. Notice. Your step affects how fine the calculation is, how many it does, right? Your range on t tells you how far it's going to go.
It looks like a piggy.
You can see this one kind of just keeps going and going. So do you guys think, even though it was a very simple polar expression, would we have been able to graph that very easily without converting it to parametric and maybe using some technology? Probably not. It'd be possible, but it'd be quite difficult. So in your book, you guys listening? In your book, there's another example about how to graph a fairly simple spiral curve with a rose, and I'd like you to look at that one. It's going to do it kind of without technology, piece by piece by piece by piece by piece. It's very annoying, so I don't give you any in your homework like that, but it's good to look at that example. So what I want to do next is use this and create the polar derivative. And that's kind of where we're going to leave off for today. So, can you guys remind me, how did we do parametric derivatives? We went dy. If we're using our parameter as theta, we'd go So what you're telling me is you know how to do that for parametric, and I just showed you how to take a polar curve and put it into parametric. So couldn't we just use that as the theory and how to compute a polar derivative? I think so. Okay, so if you have polar and want it in parametric, you go like this. So you can go straight there now. So that's what the theory is going to say. So dy d theta, what's that going to be? Can you guys help me? Let's get this out of here a little bit.
Wait, you need.
That was a specific example, right? The 1/2 came from that specific spiral curve. So now this is in general. This is polar changed into parametric in general.
Doug, you need to, with this, should it be x is cosine
Oh,
and y is sine?
yeah, I do have these backwards. You're right. Thank you, Sam. I didn't notice that. Thanks. Cool. What do I have to do to take the derivative of that?
Product rule.
First, derivative of second, plus second derivative, first derivative of second, I guess I'll be consistent, second derivative of first. That's what's on top. How do you take dx d theta? That's how you do polar derivatives, right there. So, I'm just going to have some sines and cosines that kind of sneak in there. That shouldn't really surprise you because polar functions have those all over the place. And you're going to have to take the derivative of whatever function they give you. So remember, this is all given that r equals some function of theta. So as long as r is equal to f of theta, you can do this. Let's look at one example. I don't know if I'm going to finish it, but it'll give you the idea. So let's look at one of those. Let me pause this better.